XPS is a quantifiable technique in the sense that electrons leaving the sample have a probability of arriving at the detector and being recorded, and the relationship between the electrons arriving at the detector and the electrons leaving the sample are a measure of the amount of substance. So in this case, we've got an oxygen 1s peak, and to measure the amount of substance in terms of oxygen, we have to define a background, and the background is related to the process of photoemission in a solid state. We have a peak shape that we have to integrate in counts per second EV, and this will give us a measure of how much oxygen is in our sample. However, there are a number of factors involved that determine the intensity of this peak for a given amount of substance. In the first instance, we have a physical process. There's a physical element to the intensity of a peak, and this relates to the physical process of a photon scattering electron from a particular state of this oxygen and producing an excited state. And this is the photoionization cross-section, which gives us a probability of this event occurring, and that probability will influence the intensity of the peak. So what we do is we compensate the measured intensity using Schofield cross-sections that have been calculated as photoionization cross-sections for a given photon energy, a given element, and a given electronic state. Then we have an instrument interaction with this physical process. The physical process does not emit all electrons equally in all directions, and the fact that we have an axis of the analyzer about which we can collect the electrons, and there are other directions that we do not collect the electrons, we must compensate for the fact that this distribution is not uniform, and the angle between the X-ray source and the angle of the analyzer influences this distribution. And there is an expression here and a calculated value, this beta, that depends on physics. This angle theta here enters into the calculation in terms of this polynomial in terms of cosine theta. If we choose the angle between the X-ray source and the axis of the analyzer to be the so-called magic angle, then this term vanishes and we don't have to consider this as part of the calculation of the peak intensity. The intensity of the oxygen 1s signal will be influenced by the sample itself. What happens when an electron is ejected from an oxygen atom within the sample is that the electron must traverse the sample before entering the vacuum, and en route it may be inelastically scattered, meaning that energy is lost, and therefore the electron that originally started out with the energy of an oxygen 1s electron emerges into the vacuum and is recorded by the analyzer at a different energy. And actually this is the source for the background in the XPS data. But it does mean that the oxygen 1s signal is attenuated as a function of where the oxygen is in the sample. We have a model for working out how the intensity is altered as a function of depth within the sample, and that's this exponential model, which involves a parameter a, which is referred to as an attenuation length. And if we integrate from a depth of 0 through to 3a, using this model we can arrive at a conclusion, which is that 95% of the signal will derive from the top 3a's depth of the material. So what consequences does this have for quantification? If attenuation happened uniformly over a spectrum, then the implications would be limited. However, this is not true. What happens is that this parameter A varies as a function of the kinetic energy, and here we have two formulae that estimate the attenuation length. One's based on the inelastic mean free path and the other is an effective attenuation length, and both are designed to try and measure the depth from which electrons can emerge from a sample. So we have an energy dependence, and therefore a peak that appears at a different kinetic energy from another peak will have a different attenuation, and so this must be part of any quantification of XPS spectra. The next thing to consider in terms of what alters the intensity of an oxygen 1s peak is how the instrument and the energy analyzer functions in conjunction with the lens system. When we perform a measurement using a fixed analyzer transmission or FAT mode, we specify a pass energy for the hemispherical analyzer. And this means that all the electrons that may come from a range of different kinetic energies from the sample must be retarded to this pass energy if the electrons are to pass around the analyzer and be detected. So the lens system must do a lot of work prior to taking the signal into the hemispherical analyzer, and one of the consequences of these adjustments as a function of kinetic energy is that you can potentially alter the way rays enter the hemispherical analyzer. Now, the hemispherical analyzer will accept a range of angles for these rays entering the analyzer and still have the rays strike the detector. However, as a function of kinetic energy, this may vary, and it's the way these angles vary from one kinetic energy to another as a consequence of having to retard these electrons that you end up with a potential change in the response of the instrument as a function of kinetic energy. So this is typically known as the transmission for the lens system. There's one further implication of the lens functions that vary as a function of kinetic energy, and that is that if you want to quantify spectra based on peaks at different kinetic energies, then for the quantification to make sense, you ought to have the image of the sample remain constant as a function of kinetic energy. These two images here overlaid at very different kinetic energies, and this is the ideal situation, that they both are the same size and they overlay very well. But it's not necessarily the case, that it is entirely feasible that the sample and the image of the sample that gets passed through to the analyzer may change in its distribution over the detector. You may see these two scenarios occurring, or you may have a shift. And if there's a shift or the area that's being analyzed changes in any way, then this will have a consequence for the quantification of XPS spectra. So in order to understand and relate a peak from an XPS spectrum for an oxygen 1s to an amount of substance, there are a whole range of these corrections that must be considered. So we must know how to normalize with respect to the physical process, the RSFs and the angular distribution correction, and we must know how the intensity may vary as a function of the kinetic energy related to the escape depth, the lens functions, and maybe any shifts that you may see in the image itself. And all of these are required to obtain an understandable quantification from a sample.